was
for sure.
The heat problem's number 4.
Okay.
I know it didn't give us a coefficient for what do you call it, emissivity.
Yeah.
But I mean, the light bulb usually is pretty emissive. So it's referring to the surface of the light bulb.
Mm-hmm.
Are we just taking into account convection?
Let me look at that.
Because even if, the emissivity coefficient were like even 0.5, it would still be something like 13 watts worth of power.
Mm-hmm.
I just wasn't sure if we're considering that or we're taking the emissivity in there to be like, exactly 1 or something.
Right. Which one is this?
4.
Surface of the bulb. Oh, it's cooled by a moving liquid. So this is not radiation. It's
okay, so yes, it's just convection.
Yes,
okay,
that's right. And actually, that I said that convection coefficient is sort of like a catch-all. It's not something you can derive. So that if you're using convection, that you're throwing everything in there, any kind of radiation or anything, Yeah. So yeah. I wanted to say, anybody who's interested, 3:30 today is the first design club meeting. And I thought I'd show you the start of the web page because I got it now. Let's see.
Yeah, so on the Normandale site, you're also in charge of the STEM club.
I was last year, so I'm not doing that this year. Oh, I guess so, yeah. Let me see if I can find this. Okay, so this is basically the website. It's got a main page. Eventually, this will be where you can buy stuff. Some stuff about Normandale. Anyways, the Design Club webpage is there. If you want to be hooked up with Design Club and I haven't emailed with you about it, let me know. So 3:30 today in the Fab Lab is the first meeting, and anyone who is interested but can't make it today, send me an email and I'll send you a video and notes and whatever. We did one homework question. Any other homework questions? Well, today we're going to go on to the next topic, which is simple compressible substances. What we would like is equations of state where that let us calculate properties based on other properties. It lets us that would let us calculate properties of a state based on other properties at that state. You can think of like the ideal gas law does this. If at a given state, if you know the pressure and the volume, you can calculate the temperature with the ideal gas law. One thing that we're going to use for this is property tables. Instead of having an equation, a lot of times we'll have a table for a given substance that will let us figure out, like, say we know the temperature and the pressure, it'll let us find the specific volume, the entropy, that kind of thing. Simple compressible substances are everything that we're going to do in this class. So every substance we'll discuss in this class is a simple compressible substance. It requires that the materials be homogeneous. So homogeneous means you can't go to one area of the material and measure different things in the material than in a different part. And they also have to be unaffected by electrical and magnetic fields. Okay, now this is a really important fact about simple compressible substances. For any simple compressible substance, if you know two properties at a state, that's enough to specify the whole state. So if you have a simple compressible substance and you know the specific volume and the temperature, then every other property is, there's no flexibility in what the other properties can be. You have to, there's then a specified pressure, entropy, specific enthalpy, all that stuff. It's even more restrictive in saturation states, and we'll talk about that in a few minutes. But the basic idea of saturation states is like when a chosen amount of water is in between ice and liquid. Some is frozen and some is a compressed liquid, or in between the other two states where some is a compressed liquid or some is a liquid in the saturation state and some is a vapor in the saturation state. You only need to know one property in those cases to specify the other properties. So what we're going to see is that when things are in between phases, undergoing phase change, it takes even less to figure out the state of those materials, and we'll take advantage of that. The relationships between P, so the pressure, the specific volume, and the temperature can be shown on a 3D surface called the PVT space. And there are only two of these for simple compressible substances. Well, we're just talking qualitatively about the overall shape, but every material has a slightly different surface. Like you could think of water has one of these, propane has one of these. Okay, so I'm going to put one of these up on the screen. So here's the first one. Okay, so this is the general shape of the PVT surface for almost every material. There's a different, qualitatively, there's a different one for water and anything else where the material expands when it freezes. This one, because of the direction of the volume change on freezing, you can see that this one contracts on freezing. Let's just take a second to try to get our bearings on what's going on here. So the vertical axis is pressure, the horizontal axis is volume, and temperature is increasing as you go back and to the right, as you go back. And so this whole surface does not represent a process, a single process. A process is just going from state to state to state. And each state is represented by a point on this surface. And so a process is just a line on this. And you can see that green dotted line that starts over here and goes this way represents a single constant pressure process. Okay. And so if you follow that constant pressure process from the high temperature, let's see what's going on here, okay? So start over here where my cursor is, okay? And say you're decreasing the internal energy in this material. You can see if you trace this along this line, that the pressure is staying constant, the height is staying constant, but the temperature is going down. And you can also see that the specific volume is going down. So over here, we're talking about a gas. So if you start out with a gas at a constant pressure, it's as you decrease the internal energy, you're decreasing the temperature and decreasing the volume until you get to the phase change region. And when you get to the phase change region, you get a decrease in volume as you remove energy, but no decrease in temperature. Okay. So this is the period where you're going in between a saturated vapor and a saturated liquid. Then once you've removed enough internal energy that all of that vapor has changed over to a liquid, if you keep decreasing the energy, now the temperature starts decreasing again, and the volume is decreasing again, and now we have a liquid that's decreasing temperature and decreasing volume. Okay. Follow this along here. And now this second ridge is where you're going in between solid and liquid. So once you get to this phase change point, you're at a saturated liquid. Now any decrease in energy is going into turning the liquid into a solid. There's no change in temperature, but there is a decrease in volume in this case. So you know that this can't be water, because with water, if you have a saturated liquid and you remove internal energy, you start to get an increase in volume because ice has a bigger volume than liquid water. Okay, are you with me on that? Sort of making some sense out of what's going on here. We're not really going to use this 3D plot, although it's a nice thing to make some sense out of. What we'll use is we'll use 2D projections of this 3D surface. So you can think of, like, for example, at a constant pressure, you could look at a process in a volume temperature plot, and you would see that line that traces through what we just described.
So it'd be that then projected downward onto it, just a 2D
yes,
diagram.
That's right. That's right. And I'll show you one of those in a second. Okay, this is most materials. Almost every material. And that's because the specific volume decreases on freezing. Melted metals take up more volume than solid metals. Okay. The other possibility, though, is water. So let me show that. Okay, so most of the features of this are similar when you label this. So this is for water or any simple compressible substance that expands on freezing. Okay, so let's think about a constant pressure line on this graph. So it would go something like this. And then it would trace a line like that. The difference is that little jagged edge when you go from the phase change to liquid to solid, right over here by, if you can see my cursor. Can you see that? So as you decrease internal energy in the liquid, the temperature and the volume decrease until you get to the phase change. And at the phase change, you start to change to a solid, and that solid has a greater specific volume than the liquid. We will usually use two-dimensional projections of this surface rather than the surface, rather than the 3D surface. So you can imagine, I have another picture here. So that's sort of a picture of what we're talking about. You can use orthogonal projections of this surface onto any of those planes of two. You can look at a volume temperature plot. That's the one that's not shown. You can look at pressure volume, or you can look at temperature pressure. So there's three of these projections you can use. The most noticeable and the most important feature to us of this surface, like really the one thing that you're going to have to be aware of in this class, is called the vapor dome. And it's the thing, if you look at that surface right up above, that has a sort of curved shape like that. Inside this dome is a mixture of liquid and vapor. So anywhere inside that dome for this substance is some mixture of vapor and liquid. If you're to the left of the dome, it's a liquid. If you're to the right of the dome, it's a vapor. If you're anywhere along this line on the left side, that's called a saturated liquid. So that's a liquid where if you add any more internal energy, you're going to change from a liquid to a gas, a vapor. And on the other side, you have a saturated vapor.
Is that a 2D projection onto pressure volume?
It's sort of a 2D projection, just looking straight down perpendicular onto like standing on the volume side, kind of looking diagonally down onto the dome, just looking at that feature. So it's not really onto any of those projections, but you can see it in these different projections, and it sort of has a different shape in each one, you know?
Yeah, it's just that general contour on the
Yeah,
diagram.
right. And this point right here is called the critical point. That's not going to be a super big deal to us, but I will define that. And this line is called the triple line. Okay, so let me give you definitions of some of these features. So first, the triple line. For any point along that line, the solid, liquid, and vapor states exist in equilibrium. The second definition is the critical point. And that is a pressure and temperature above which there's no distinction between a vapor and a liquid. So no distinction exists between a vapor and a liquid. Once you have a pressure and temperature higher than the critical point, this is called a supercritical fluid. The next one is a saturated liquid. And a saturated liquid is liquid, but any more internal energy that's added changes it to a vapor. So if you're thinking of constant pressure, that's liquid at exactly the boiling point. And a saturated vapor is the same idea. So that is a vapor where any decrease in internal energy changes it to a liquid. And then the region that says vapor, if you go up there and you get to a higher temperature, you get to a vapor that's a higher temperature than the boiling point, that's called a superheated vapor. So a superheated vapor is vapor above its boiling point. Okay, well, let's look at a temperature volume diagram to see what happens during a phase change. So this is a phase change. And the one we're going to be interested in is between liquid and vapor. And we're going to look at it in a PV diagram. That is not the one I was hoping for. But I guess that's okay. Okay, so let's see what's happening. So you can see the vapor dome there in the middle. That represents the phase change between liquid and vapor. If you're on the left there, you have all liquid. And when it reaches the edge of the vapor dome on the left, that's when it's a saturated liquid. And so following one of these two lines, and remember, a process is just a line. It's not this entire graph. So one process is one of these lines. So start over here on the left, and as you add internal energy, you have a liquid, and you're increasing the temperature, increasing the volume, until you reach, and these are for a constant pressure. This is what a process looks like with constant pressure. So you're increasing the temperature, increasing the volume, and you get to the saturated liquid point. You get to the boiling point. And once you're at the boiling point, any internal energy you add just little by little switches this material over from liquid to vapor. It doesn't increase the temperature at all because saturated liquid and saturated vapor have the same temperature. Okay, and so as you keep adding energy, this is the one region, and also the phase change between solid and liquid. But these phase change regions are the only places where you're adding internal energy and not getting an increase in temperature. Okay, and so you get more and more vapor and less liquid as you add internal energy until you get to this point where the entire material is saturated vapor. You're still at that same phase change temperature, but you don't have any liquid left. And then at that point, if you add any more internal energy, you start to raise the temperature of the vapor again, and you have superheated vapor, and you start to increase the volume and temperature again. There is a big difference in volume between a saturated liquid and a saturated vapor. So as you're adding energy to a saturated liquid, what that energy is going into is making those molecules move apart, and they move really far apart. And once you get to the point where all of those liquid bonds are changed, and now you just have a gas where you have molecules just bouncing around, then from that point on, all you're doing is increasing the temperature and volume as you add more energy. Okay, so let's talk about this and this, okay? So to get from the left side of those two regions to the right side, you get that by adding energy. And the energy difference between a saturated liquid and a saturated vapor is called the latent heat. Okay, that's the amount of energy that you can add to that material without changing its temperature. The amount of energy you can add to a saturated liquid without increasing the temperature. That's going to be a hugely important thing for engineering applications of thermodynamics. And I'll give you a little example, to try to explain why that is. The same thing happens, so that same phase change phenomenon happens when you go from solid to liquid, but the change from liquid to vapor is a lot more important, and that's because there's a lot more latent energy that goes into the phase change from a liquid to a gas than goes into the phase change from a solid to a liquid. And how much energy you can put into a saturated liquid before it starts changing temperature is really the key thing that makes this valuable, okay? So all of these things that you can do with the phase change from liquid to vapor, you could do with the phase change from solid to liquid. It wouldn't work as well because it's not as much energy that goes into it. Okay, so let me try to explain why this is, try to understand why this is going to be a really useful thing for us for power cycles, refrigeration cycles, okay? The latent heat energy that goes into a saturated liquid without raising its temperature is very useful. So to explain that, notice that the way that we are going to add internal energy to a material is often going to be through heat, okay? Like you'll light a fire under something or whatever. You have an outside source of energy that has a higher temperature than your material, okay? So we're often adding energy to our system using an external high temperature region. So the question is, how much energy can a high temperature region add to a system if, let's say, your system has a temperature of 80 degrees Celsius, and that outside source has a temperature of 120 degrees Celsius. Okay. If there's no phase change going on with your system, then every bit of heat that comes from that 120 degrees Celsius outside region is raising the temperature of the inside. And as those get closer to the same temperature, that heat transfer happens more slowly. And eventually, when you get to 120 degrees for your system, no more energy can go in, right? So you're limited by how much energy you can put in there. If, say, at 100 degrees, there's a phase change that happens, then when this gets up to 100 degrees, all of a sudden you can start pouring energy into your system without making that energy transfer any less efficient, you know, because the key, how much energy you can put in per second has to do with the difference in those temperatures. Okay. Are you with me on that, or?
Yeah, the rate of change in the energy is based off of
temperature
difference, not based off of whether or not it's going through a phase change.
Think about it like this, instead of thinking about, so think of it as like, this one's 81 degrees, okay? And the system is 80 degrees. If there's no phase change happening at 80 degrees for the system, okay, you get a little heat energy from the outside to the system, and the system goes up to 81 degrees, and that's the end of any energy transfer, okay? So how much energy can you put in? Basically none, you know? But if there's a phase change at 80 degrees, and this is a liquid at 80 degrees, you can pour in all the energy that it takes to raise the temperature, to change the liquid from liquid to vapor, and the temperature stays at 80 degrees, so energy keeps going into it. And it's only after all of that liquid becomes a vapor that the temperature of that vapor will start to move up to 81 degrees and end the ability to transfer energy. Okay, so all of that latent heat can be added before you have those temperatures equal each other. Yeah, right. That's like the key thing is that during that phase change, the temperature does not go up. And so you can, and it gives engineers the ability to put a lot of energy into liquid without raising its temperature. And not raising its temperature makes heat transfer happen much more efficiently and for longer. Yeah. Any other questions about that stuff? So I guess the bottom line here is not much if there's no, so how much energy can the high temperature region add to the system if these are the temperatures? Not much if there's no phase change. But a lot if there's a phase change. Okay, so for a lot of our simple compressible substances, we're going to use property tables. So let me start talking about property tables. So there are three forms of tables, three types of tables. So the first one is saturation tables. Those are the easiest ones to use. So whenever you're dealing with a liquid or a vapor at saturation, finding out values is easier. At saturation, one property is enough to specify the entire state. Remember I said that in general, for a simple compressible substance, two properties are enough to specify the entire state. But if you're at saturation, it only takes one. And so what that means is that if you're trying to look something up in a table, if you know the substance is at saturation, you can do it by just temperature or just pressure. On the other hand, if you're trying to look up values for a substance that isn't at saturation, it's a superheated vapor or a compressed liquid away from the phase change, then you have to do it as a two-dimensional lookup. You have to look it up as a pressure and a temperature to find the specific volume, for example. And that's a little more difficult to work with. So the saturation tables, since you only need one property to specify the state, can be indexed by the temperature. And you have to know whether you're dealing with a saturated liquid or a saturated vapor. So they're separate tables. God, my stylus is going wacko today. So separate tables for saturated liquids and saturated vapors. We'll also use tables that are indexed by pressure. And again, there are separate tables for saturated, liquid, and vapor. Like I said, these are easy to use, the easiest ones to use, because you're looking up by a single value. And the nice thing is that for engineering applications, most of the properties that you're looking up are for saturation states, because that phase change region is really where you always want things to be. A term that we're going to use a lot is quality. And quality is, it's basically how much of the material is vapor compared to liquid. So the quality, we'll use the letter X, and it is the mass that's in the vapor state divided by the total mass, which is the mass in vapor plus the mass in liquid. And so that quality X, it tells you something about how much energy is stored in that material that the temperature doesn't tell you. Okay, the temperature is the same no matter how much is vapor and how much is liquid, but the quality, if the quality is high, there's a lot of energy stored in it. If the quality is low, there's not much energy stored in it. If your system is all vapor, then X is equal to 1. And if your system is all liquid, then quality is 0. Okay, so those are the easier ones to use. Those are the saturation tables. So that's one of the 3 types of tables that we'll use. The second one is a compressed liquid table. And these we have to look up by pressure and temperature. And the way we do that is they're grouped into different pressures. And inside that group for that pressure, you look it up by temperature. So they're separated into sections by pressure. And then within that section, they're indexed by the temperature. And then the third type of table is a superheated vapor table, and that works just the same as the compressed liquid table. So that works like the liquid tables. That means you find the section that has the pressure you want, and then you look through the temperatures. There is a problem, though. What we'd really like is we would like to have equations where we plug in the pressure and the temperature, say, that we want, and it gives us the specific volume. Because in a table, you don't have infinitely many values, you know? So if you want to deal with a pressure of 1.25 and a temperature of 87 degrees, and your table only has pressures of 1.2 and 1.3 and temperatures of 85 and 90, what do you do for the properties that you want? And the answer is you have to do linear interpolation to find the values you want. So basically, whenever you're using tables for properties, you're going to need to use linear interpolation. And the idea of linear interpolation, it's not just for thermodynamics tables. It's a useful thing whenever you're given a finite set of data points. So if you only know function values at a finite number of points, this linear interpolation lets you approximate function values in between those. And here's a picture of how it works. So if this is your independent variable, and this is your dependent variable, I'll call it f of x. So these are just totally general. We're not talking about specific properties or anything right now. And let's say your function looks like that. But you're not given the function. You're only given the function values at these points x1 and x2. Okay. And you want to know what the value is at this x in between. It's called linear interpolation because you approximate it by the value of the function in between those 2 points. You assume that the function is linear in between those 2 points. And as long as your points are close enough together, and as long as this function isn't oscillating too fast, you get reasonable approximations. So the way this works is the function at x that we're trying to approximate is equal to the function at x1 plus the function at x2 minus the function at x1 divided by x2 minus x1. And then last, multiplied by x minus x1. So this is just the formula for that over there. We start with the value of the function at x1. Then we assume that in between x1 and x2, the line has this slope. And then we go along that line the distance from x1 to our desired x. Okay. So that's a linear interpolation. Let's just do it on do an example with a random function. So let's use linear interpolation. To approximate the function x squared at the point x equals 2, given that what we know is the value of the function at 1.5 is 2.25, and the value of the function at 2.5 is 6.25. Well, since we made up this example, the function is x squared. And so we know that the thing we're trying to approximate, it should be close to 4, hopefully, if this works out. But what we're imagining is that we don't have the function, we only have these finite data points. And we're trying to come up with our best guess for what the function value is at x equals 2. Okay, so let's use that formula. So the function when x is equal to 2 is equal to the function when x is equal to 2.5. So that's 6.25. Minus the function value at 1.5. So that's 2.25. Yes? Yep, you're right. Yep. So first, the function value at 1.5. And now divide by 2.5 minus 1.5. And now multiply by how far along that line we go from 1.5. So that's going to be 2 minus 1.5. And so you get 2.25 plus 4 divided by 1 times 0.5, and you get 4.25. It doesn't give you an exact answer, but it was in the right ballpark. It was closer than either of the two endpoints. And the closer you pinch those two values, the closer you can expect your interpolation to be. So if we did it with the points, with the function values at 1.9 and 2.1, we would have been a lot closer. Okay?
So like a property table that has really far from
well, yeah, I mean, I guess it depends how close to linear it is. If it's very nonlinear, then it would be pretty close to useless. If the curvature is pretty small, then maybe you'd still get good values. All right, well, with this way of doing linear interpolation, so notice that we have one independent variable here. Notice that what I've showed you so far here would only be useful for the saturation tables because those are the ones that have one independent variable. you look it up by temperature or pressure. Okay. So what do you do in the case where you have two independent variables, like you would for a compressed liquid or a superheated vapor? Okay. Well, you have to sort of do it in steps then. And I'll show how to generalize this to 2 dimensions next time. But just notice for now, with this interpolation of one independent variable, we could only look up values in saturation tables. So we'll generalize to 2 independent variables next time. Yeah, and like I said, this idea of interpolation is a super important idea for really any numerical, like any kind of computer program that you use to do calculations. And so it's a good thing to get used to and to make sense out of beyond just our use in property tables. Okay, that's all.